Hello, welcome to Practical Electronics. Today we'll be talking about bipolar junction transistors, or BJT for short. A BJT resistor is formed by joining together two p-n junction diodes in series that share either a common P or N terminal. In this case, we have it sharing a P terminal, positive. Combining the diodes produces a three-layer, two-junction, three-terminal device, either NPN, which we have here, or PNP configurations. The pins are labeled as emitter, base, and collector. Base, collector, emitter. And transistors can act as either an insulator or a conductor, depending on the application of a small signal voltage. The transistor's ability to change between these two states enables it to have two basic functions, which we'll look at: switching or amplification. First, we'll look at the BJT as a switch. So, this drawing we have the base, the emitter, the collector. Coming into the base, we have 3.3 volts supply coming from a battery with resistor, a 2.6K resistor. So that gives us 1 milliamp current coming into the base. The collector, we just have a battery source, another one, and the emitter is going to ground. Okay, so for a BJT transistor to act as a switch, it needs to be in saturation mode. Saturation mode is when the base current reaches a level such that any increase does not increase the collector current. First off, to calculate this 1 milliamp of current coming into the base, we just take 3.3 volts, our supply voltage, minus 0.7 volts forward voltage of the diode in the emitter. That'll give us 2.6 volts. Now, with V equals IR, Ohm's law, we can calculate 2.6 volts over 2600 ohms will give us 0.001 amps, or 1 milliamp. So, with this transistor in saturation mode with 1 milliamp, we need to calculate our emitter current. To do that, we get the beta of the transistor, which can be found on the tech data sheet. So for this 3904 transistor, it has a beta, which is represented by either a B or this H subscript Fe of 100. And the current is equal to this formula, which is the base current times beta. So IC, which equals base current times beta. And remember, IC always equals IE. Therefore, IC or IE equals IB 1 milliamp times beta 100, which gives us 100 milliamps flowing from the supply at C down through the emitter. Okay, now we'll have a look at a BJT transistor as an amplifier, AC. Start off, we'll have a small AC signal coming into VIN. This causes the exact same magnitude AC signal at the emitter. Now, if the voltage at the emitter resistor increases due to the AC waveform here, due to the AC waveform at the base, then the emitter current also increases proportionally due to V equals IR. So V increases, R is a constant, then this emitter current will also have to increase. Now, with this transistor, remember, the current at the collector always equals the current at the emitter. So, if this current increase will also appear at the collector. If our collector current goes up, our resistor at the collector is constant, then the voltage drop across this resistor will also increase. So to calculate our gain, we know that delta VC is equal to delta IC times RC. And in this case, it's negative delta IC because of our voltage drop, which we explained previously. So to rearrange it, we know that IC is equal to VE over RE due to Ohm's law and the fact that IC is also equal to IE. To rearrange it further, we switch RC and this delta VE, so we have RC over RE times voltage in, because our VE is equal to our V in to give us our gain. So remember, for this gain, this negative simply denotes that it'll be an inverting op-amp or an inverting gain, which means that the signal will be in 180 degrees phase.